Welcome everybody to the second part of the lesson 4 of the LTCC course on maximum entropy model for networks. We have seen in the previous class how it is important to go behind the degree constraint that enforce only the degree sequence, and how nonlinearity can cause phase transition, structural phase transition in network ensemble. Here, I would like to go behind the constraint of the degree sequence, exploring another direction, mainly considering the interplay between network structure and latent variable. And I will frame this in a general context, but then specifically have in mind spatial network intended in a quite of a general sense. So nowadays, network data comes together with a variety of metadata, and these can include affiliation to different administrative and local organization for the internet, for social or also metadata on the links like traffic, for transportation network, or just the distance between the position of distance between two nodes in transportation network. And in social network, there is a lot of metadata about the nodes, and this might include a social distance between the nodes, or pseudo distance between the nodes. And in biological network also, you can have a lot of information about the node. For instance, in disease, you can have the lethality of a disease, or in a protein network also the lethality of a protein when it's knocked out from a cell. So in many cases, we have information about metadata, but in some cases we might want to infer. So we might want to infer a classification of nodes, for instance, that reveal a community structure in the network. And this is done by inference in a network, or an inference of the political distance between blocks and things like that. As a problem of inference, there is also this beautiful problem of embedding a network into space. So if you have a network data and you don't know the coordinate of the point, you might want to visualize by embedding the network into a space and choosing the best coordinate of the node in this network. And this is a beautiful picture coming from the cover page of Nature for the 150 year of Nature, coming from the group of Laszlo Barabasi, in which you can really navigate the network. And in order to do that, you need to solve very challenging inference model. However, if you want to study, this inference model, you should have at least a very good understanding of the direct problem, in which you want to measure, to generate network given a set of latent variable, which you can also call hidden variable. And here you assume that the latent variable are known, and you can construct the network given this latent variable. And here we will cover this with special attention to kind of a generalization of spatial network. And we will focus specifically on the canonical network framework. So first of all, we start from some local constraint. So constraint depending on a structural property of the network and the latent variable, but defined from the bottom up. Okay, so we will consider a spatial network intended in the general meaning, in which we have n node, and every node is assigned a position or a vector indicating some feature of the node. And this position can be actual position, geographic position of node in space, or a position of node in a generalized space, for instance, a social distance in a network, or in a, or any pseudo distance you might want to define. It doesn't need to be exactly a distance. So we consider the bottom-up approach, in which we have local constraints. So we constrain the degree of each node in expectation, in a canonical ensemble, and we constrain the expected total number of links at distance d. So we can consider all the links with adjacency matrix element equal to 1, provided we have this characteristic function that impose that the distance between the two latent variable associated to the node I and node J are in a given bin, so between distance d and d plus delta d. Okay, so and we fix this constraint for every bin, for every distance interval in average over the ensemble. So according to the maximum entropy network ensemble, the probability of a graph given this latent variable that are assumed to be known is given by this exponential form when we have a local Lagrangian multiplier. So Lagrangian multiplier enforcing the degree of each node for each node I, and the number of links at distance d for every bin of distance d. Omega delta, omega d. So if we have this exponential form, we can also change the order in which we perform the sum between I less than j and d. And by expressing omega dij as practically the Lagrangian multiplier associated with the bin in which the distance dij belongs, we can write this exponential Gibbs measure in this form. And then using the same steps using the canonical network model, we can actually consider only independent link, so only link connecting node I and j with I less than j, because here we are considering simple networks. So when we have a triangular upper triangular matrix, we know the upper lower triangular matrix. Then we can write this Gibbs measure as the sum over this as an exponential was Hamiltonian, is given by the sum over I less than j of lambda I plus lambda j plus omega dij. So we have an additional Lagrangian multiplier depending on the pair, on the distance between I and j, and then all these multiplied by Iij, the adjacency matrix element. So as you see here, the Hamiltonian is linear in the adjacency matrix. So the marginal is simply given by this expression, and you can impose the constraint to the expected degree as the sum of the marginal of the expectation of all the links of node I. So we sum over all j between 1 and n, the marginal Pij. And the other constraint, the constraint that we fix the total number of links at distance d, is enforced by this. So in average, so is enforced by this. So we sum over all pair I and j of the probability that I and j are connected if and only if the distance between I and j follows in the bin d, corresponding to the distance d. So if we have this expression and we consider a function that is a function only of the distance between node I and j, which is e to the minus omega dij, then the probability that I is connected to j depends on a variable theta I, a variable theta j that depend only on the Lagrange multiplier enforcing the degree of node I and the degree of node j, and then they are modulated by this function w, which is a function of the distance between ij. And this function is quite important to define, to modulate and to the probability that I and j are connected given the latent variable and given the distance between node I and j. So here we took the airport network in which you have airports that are connected by flight connection in US, so you know the coordinate of the network, and by imposing this bottom-up constraint, you can find this Lagrange multiplier omega d and ultimately the function w of d. And you find this function which is consistent with the, for large enough distance, with the power law decay of the distance. And if you reshuffle the node position and you do the same thing, you see nothing, you know. So this means that really this function is non-trivial and take into account the real position of node into space. So here you notice that you find this very neat trend for distance large enough, and for small distance you find a cutoff, because practically for most distance there is no enough incentive to have flight connection at small distance. Actually, there are some flight connection at small distance, really connecting very small island, but so so we checked this also in other countries, and in particular in the Indian train and airport transportation network. So this is the airport network, this is the transportation network, and then we have considered also the rail airport connection, and we have measured this W, and for the rail, airport, and airport rail, we find always this kind of consistent power law behavior for large enough distance that seems quite robust. And later on, when we will cover global constraint, we will see that there is an interpretation of this finding in terms of the cost of the links. So here we will cover, we attack the problem of considering a global constraint. So before we have a bottom-up constraint in which we want to constrain the number of links at a given distance. Here we have a global constraint. So we consider always some latent variable associated to the node that can be indicate a position in space, a classification, or a proxy for a degree of the node. And we consider a payoff function, so a function that indicates the cost of the link or the benefit, depending on what side do you prefer. And it is the payoff or the cost of a link between a node of latent variable x and a node of latent variable y. So we take a canonical approach and we take global constraint. So the global constraint is the expected total number of links or the expected total number cost of the link, payoff of costs of the link. So we here, this is the familiar form enforcing the number of links in average, and this is the expected total payoff of the link. So here you have every link, and you weight every link you have with the cost function that you have chosen. So the maximum entropy ensemble in the canonical approach will give you a Gibbs measure. And here we have Lagrange multiplier beta and mu, which are global. They don't have indices I or ij because they enforce this global constraint. And we fix the expected number of links and the expected cost of all the links we observe in the graph. So here we can calculate, here this Hamiltonian is linear in the adjacency matrix. So we can calculate directly the marginal probability of observing a link between node I and j in terms of the latent variable of the node. And this takes this very familiar expression nowadays that we have here, where we have the Lagrange multiplier, the cost of the link between node of latent variable xi and xj, and mu, which is the Lagrange multiplier enforcing the total number of links in the network. So what happens if the scalar variable, the latent variable is scalar? If the latent variable is scalar, then we have this marginal Pij, which is only dependent on the latent variable of node I and the latent variable of node j. Okay, so the probability that two nodes connect only depend on the latent variable on I and the latent variable of j. This is, for instance, can be the example where you have different countries with different GDP, and you assume that the trade between this country, the network of trade between this country, as a probability of the link that only depends on the GDP of these countries. And in this case, this latent variable xi acts as a proxy of the degree, is a function of the degree, because in fact, if you impose an expected degree for each node, you see that the expected degree of each node only depends on the latent variable. Okay, so the latent variable becomes a proxy of the degree in this case. And in particular, if this function, for this function of the cost of the link, you take something of this type, so the sum of two function, one depending only on xi and the other depending only on xj, the same function, one only depends on calculating in xi and one calculated in xj. Then by putting theta xi equal e to the minus lambda xi, you see that the marginal distribution now reduced to this form in which you have practically lambda of xi act as a Lagrange multiplier enforcing the degree of a node in an ensemble in which you have an expected degree sequence. So here we are enforcing a global constraint, but the cost of each link as this form of a sum of the function calculated at xi plus a function calculated at xj, and then the marginal distribution becomes practically reducible to the marginal of an ensemble in which you have a given expected degree sequence. So really here, this latent variable act as can be thing that you measure. That can be the GDP of a country, there can be other information about the node. So this model actually provide an interpretation in some sense of the model in which you enforce the expected degree of each node. So this latent variable can be the GDP of the country in the World Trade Web. They can be asset and liability in financial bank, financial network, or any variable that can be considered a good proxy for the degree of the node. or a variable associated with the degree of the node. So this is another way to interpret the network ensemble with expected degree sequence. So now we want to add some more spatial component, and then we can take a cost of the link that now depends on this sum of a function lambda calculated at xi and a function lambda calculated at xj, but also might depend on a function omega that is a function of the distance between the latent variable of the connected node. And for this function of the distance, we can take a function that grows like the logarithm of the distance. So that is a payoff that is linear in the order of magnitude of the distance between the node. Or you can take a payoff that is linear on the distance, or any function you should like. But these are two main functions that are a good reference to get an intuition of what we mean. So if we have this choice of the cost function, so depending on a variable only associated to a single variable one of the node I, and then calculate the same function calculated for node j, plus a function depending on the distance between the latent variable, then we can do a transformation of variable, and the marginal distribution now becomes a function of a variable that depends only on the latent variable of node I, a function that depends only on the latent variable of node j, and these are functions that effectively constrain the degree of node I and the degree of node j, and then a function of their distance. And interesting, this function of the distance is defined in this way as e to the minus beta omega, when omega is the payoff that we associate to the link connecting node at distance d, at different distance d. And then if this omega dij grows like the logarithm, so the cost is associated to the order of magnitude of the distance, then we have a power law decay of this function with the distance between the node. If omega dij is linear on the distance, then this w decay as an exponential decay of the distance. So here, with this global constraint, we have obtained an interpretation of the power law scaling of this function w that we observe in the bottom-up approach when we, in the airport network, we see that this marginal is modulated by a function that is power law of the distance. So the observed power law decay WD of the American airport network and the Indian train and airport network can be interpreted as the outcome of an effective payoff of the connection growing proportionally to the order of magnitude of the distance between the nodes. So it's like if we are uncovering that actually there is a global optimization there that is performed there, which is assuming that effectively the cost of a flight connection increase like the logarithm of the distance between two airports. There are also different type of constraint. For instance, this constraint in which you have the distance between this payoff function, in which we have the distance between the two nodes I and j minus r0. And if you calculate the marginal probability associated to this cost, you see this function, which is a well-known Fermi-Dirac function. And then as a function of beta, if beta is infinity, this function becomes a step function. So practically the probability, the marginal probability is 1 for pair of nodes at distance R0 or less, and 0 for node at distance greater than R0. So these are random geometric network in which all the nodes at distance less or equal R0 are connected to each other. And when beta is decreased, it's not infinity, but is finite and decreased, this probability of connection is smoothed out. But still, as beta increase, this distribution becomes sharper and sharper. And this random geometric graph have been studied a lot in the mathematical and network science literature. And this brings me to a very popular model of random geometric hyperbolic network that has been proposed by Bokunia and Kryakov more than 10 years ago. In this, this model is a canonical network ensemble in which you have a random geometric graph, a soft random geometric graph on hyperbolic space. So the nodes are placed in a hyperbolic Poincare disk where the nodes have a radial and angular coordinate r and phi, and two nodes of coordinate r and phi in here in a Euclidean interpretation of this disk. Then they are endowed with a hyperbolic distance, where this hyperbolic distance is a function of the radial and the angular coordinate according to this expression. And then for very small phi, sorry, this is phi, you can approximate this distance in this way. And this is the approximation used by Bokunia and algorithm. And this model you can take you taking this expression for the distance, you can take a cost or payoff function, which is the one of the soft random geometric graph, so the distance minus R0. And by plugging in the expression of the hyperbolic distance, you have this relation. And then you can really set mu equal to 0, because you can absorb any value of mu into R0 actually. And then the marginal probability, the probability that I connects to J, can be expressed in this way. So now, by considering the expression for the hyperbolic distance given by this equation, and setting theta I e to the minus beta zeta r, the radial distance of node I minus R0 half, and setting W as a function of the angular difference of the angular different of the angular coordinate of the node, we have that W is going like a power law of the angular distance between the node. So when you have here in the marginal, this is exponential, this is theta I, theta j, delta of phi ij to the minus beta. So this marginal probability takes the shape of a marginal probability of a maximum entropy ensemble in which you have a constraint on essentially on the expected degree of I, expected degree of J, and you have a modulation, spatial modulation with a distance, with the angular distance between the angular coordinate, which decays as a power law. So the random geometric hyperbolic network model reduced to the maximum entropy model with given expected degree sequence and a cost of the link proportional to the logarithm of the angular distance between the nodes. So this power law decay that we are also seen in the airport network. So, and here really you see that this theta variable is associated, is a proxy of the degree of the node, and because the expected degree of the node is given by this expression, right? So if you are in a sparse network limit and you neglect this term at the denominator here, you see that the degree is proportional to theta high. So therefore, the degree is a function of the radial position of the node in space. So, so what we do in the sparse electron limit is that we neglect this part at the denominator and we assume that K is proportional with theta. So practically we can say that K is proportional to e to the minus beta zeta r. Is proportional to e to the minus beta zeta r. So what is the relation between the node distribution, the radial coordinate of a node is practically in this sparse regime associate a proxy of the degree of the node. So what is the relation between the node distribution in this hyperbolic space and the degree distribution? So if you assume that this relation is valid, then we can go from the distribution of K to the distribution of radial distribution of the node just by using the formula for changing the variable from K to R, when K and R are related by this expression. And then practically, if we want to have a radial distribution that enforces a power law degree distribution for a power law exponent greater or equal than 2, then we see by this changing this variable that the radial distribution of node in space should be exponential. So this is a prescription of how to get a power law network in this framework is to have nodes distributed radially in this hyperbolic space according to this exponential distribution. So this is a way to relate this model, hyperbolic model in geometric model with soft constraint to the maximum entropy ensemble, spatial entropy ensemble. So practically the effectiveness of this model in capturing a real network is supported by the fact that this model is just reducible to a model, a maximum entropy model with constraint on the degree of the node and on the node at a given distance, number of links at a given distance. So the final remark, so in this class we have covered maximum entropy network ensemble that describe network ensemble with latent variable, and we have focused mostly on the spatial interpretation of this latent variable, and we have followed a bottom-up approach, so how to go from a network and enforcing the degree sequence and the total number of links at a given distance. And then we have considered instead a top-down approach in which you consider a global cost of the links, and we have covered a soft random geometric graph and in any space and in the hyperbolic space in particular. Thank you so much for your attention.